in exactly without having a metaphysics of probabilities, as an account of what probability is. Boltzmann didn't really say what probability is, and most physicists will not say what probability is, or if they do say something, they say something which is easy, to I don't know, to show it can't be what they really mean. It's a big, interesting issue, exactly what counts. What makes probabilistic claims true or false? Heather, in fact, we'll talk about that later. I'm not going to say anything about that actually in this talk. I'll leave it to Heather, whose views are completely different from mine, but we will see how that goes. Okay, so Boltzmann had this idea, talk about the probabilities of the microstates that realize a macrostate. Macrostate means ice cube in water at a certain temperature, certain size ice cube, certain density, certain temperature of the water, and so on, certain amount of water. He gives an argument, and people in statistical mechanics have refined arguments in this form, that from the assumption that there's a certain kind of probability distribution over the microstates that could realize that macrostate, could make that macrostate true, implement it, you get the conclusion that the evolution of that system will be towards higher entropy and not be towards funny things like the ice cube going and leaving the room in different places. Here's a pictorial way of seeing what's going on. This is supposed to be, Maxwell's demon is a little bit more complicated kind of situation, but Maxwell had this idea that you can see that this must be a probabilistic law. Imagine a gas, let's say in two chambers with a little door, there's a little demon looking at the door. One side is a gas, let's say, that's cold. Its molecules, its atoms are moving slowly. On the other side, it's hot, moving fast. As you know, that as entropy increases, the temperature becomes equalized. So all the fasts in any location, there are as many fast-moving and slow-moving, fast and slow-moving molecules, so they stop bumping into each other, so that their motion sort of evens out. It becomes a kind of Gaussian distribution. But in any case, imagine first that it's not like that. Fast-moving on B side, slow-moving on the A side. You could see that if this demon here could tell which are the fast and which are the slow ones, he could actually get more fast ones on one side and more slow ones on the other side, right, by opening and shutting the door at the right times. That would be a Maxwell's demon if there could be such a thing. But even if the demon put a blindfold over his eyes and just opened and shut the door at various times, you can see that there will be, by accident, by chance, a certain chance of his increasing the entropy. Of his decreasing the entropy, right? Rather than it's increasing, because most of the times he does it by opening and closing the door, and the temperature's going to be evened out. But sometimes it won't. And so you can see that the second one really has to be probabilistic. That's a nice argument. So Boltzmann introduced this idea, and Boltzmann said, great. I don't know what he said right afterwards, but he thought he felt really great, I assume. But then a little bit later, Zermelo and Loewer and some various other people said, not so fast, Mr. Boltzmann, Professor Boltzmann, because if you make inferences from your assumption of uniform probability, not towards the future, but towards the past, you also get that entropy increases towards the past. And that would be ridiculous. That would mean, for example, that the ice cube was bigger in the past, likely bigger in the past rather than smaller, and we don't think that. So this leads to a so-called reversibility problem in statistical mechanics. A lot of attempts to solve this. The history of the subject is strewn with failed attempts, I think, but there are many interesting ideas. When I say these failed attempts, there's always a few people in the audience who thinks one of those things I think is a failed attempt is a great success. Maybe we'll talk about this later. But Reichenbach had ideas about this. Boltzmann himself did. In fact, Boltzmann really had ultimately the right idea. Popper thought that the right thing to do was to change the fundamental dynamical laws, and quantum mechanics did that by introducing propensity probabilities, and Popper was totally messed up about all of this, but whatever. Another way is to be like Mach was, a kind of instrumentalist about the probabilities. There are people who are like that. We're totally some of us know, of course, Steve Leeds is like that, some other people. I don't like those solutions. But there is a solution that's getting more widespread. It's already implicit in Boltzmann, really. And other people have it. And its history is not so clear, because when you go around asking people who, real people who do statistical mechanics, I have a colleague called Joel Leibowitz, who's one of the big names in physics and statistical mechanics. He has a view like this, and he says, well, I always thought that. So exactly where it comes from, I'm not sure. Richard Feynman, surely you're joking. I hope not about this. Mr. Feynman has this view, and some of you may know or not know, it's a little book by Feynman. Feynman hated philosophers, incidentally. And I think that this book contains a lot of philosophy. It's lectures he gave at Cornell, where the philosophers he met were Wittgensteinians. So that's my explanation of why he hated philosophers. But, so he has a lot of negative things to say about philosophers, mostly ill-conceived, I think. But he was a very smart philosopher as well as physicist. He introduces this idea, but with no fanfare, it's just an obvious thing. And the idea is, it's rather astonishing when you really take it on board, that if you're going to solve this problem of having real probabilities, and it's going to solve the problem of reconciling thermodynamics with classical mechanics, same with quantum mechanics, what you have to do is to not introduce the probability distribution, piecemeal, for this system at this time, that system at that time, but you got to introduce it for the whole universe at a particular time. And the only time that makes sense to do that is at or right about the origin of the universe. This has gotten to be known the past hypothesis. Detailed arguments for this being the right way to do it are now around in various places. Also, objections are around. The first extensive discussion of this that I know of is in a book by my colleague and friend David Albert called Time and Chance that was published about 12 years ago. Sean Carroll, some of you may know about, is a physicist at Caltech. He has a book with a great title. It's called From Eternity to Here. He presents a lot of physics. He's one person in physics and cosmology. But he develops this idea with due reference to David Albert. But the idea goes back, like I said, you can find it in different places. So here's the idea, that if you want to really give laws of, describe our universe, as I was saying, a theory of everything show, one of the things you'll have to introduce is a probability distribution over the possible initial micro-conditions of the universe. The idea is, there's an initial macro state. Of course, exactly what it is, we know a lot about, but we don't know enough about. Really, we more need to know. But we know that the universe was once very small, 10 to the minus 50-something seconds, 33 seconds, whatever the right question says. It was very small, it was incredibly dense, it was unbelievably hot. The matter of it was more or less uniformly, well, there wasn't any matter actually, it was a field, but it was a field of a sort in which gravitation hadn't yet played any role. It was about to. So there are ways in which physicists know how to describe this. But of course there'll be many microstates, mechanical states, which make this macro state true. And that there is such a macro state is kind of the result of cosmology. It's an amazing story about how, the red shift led to thinking that the universe is expanding, and so it must have been in a much smaller situation at some point. Much more detail has been found out about that. The expansion was very, very rapid at a certain point at the beginning, and is accelerating now. So there's not totally known, I think, but there's a history of the rate of the expansion. And the background micro-radiation that is evidence for this Big Bang state, and the constitution of the stars that is also evidence for this background state, and so on. So there's a lot of evidence that converges on this picture, and it's just the picture that's needed, together with the uniform probability distribution, to get the second law of thermodynamics holding its probabilistic